Muy buenos días para todos y todas. Bienvenidos a este webinar. En el día de hoy, en estos encuentros académicos del capítulo estudiantil del American Concrete Institute de la Universidad Nacional de Colombia. Les voy a leer el orden del día. Primero, daremos las palabras de bienvenida en español y en inglés. Segundo, la presentación del ingeniero Richard Tomasetti en español y en inglés. Tercero, la conferencia titulada Why Concrete for Tall Buildings, en inglés, a cargo del ingeniero Tomasetti. Cuarto, abriremos un espacio de preguntas y respuestas en inglés con el señor Tomasetti. Quinto, unas palabras de cierre en inglés. Sexto, final del evento. Entonces, comencemos. Muy buenos días a todos y bienvenidos a los encuentros académicos del capítulo estudiantil del American Concrete Institute de la Universidad Nacional de Colombia. Permítanme presentarme, mi nombre es Edgar Nicolás Fuentes Alfonso, soy ingeniero agrícola e ingeniero civil de la Universidad Nacional de Colombia, sede Bogotá, y actualmente curso la maestría en ingeniería de estructuras en la modalidad de investigación. Me desempeño como ingeniero de diseño de la firma Santander y Asociados y soy miembro del Council on Tall Buildings and Urban Habitats, CTBUH, donde hago parte de la Asamblea de Materiales. Además, tengo el honor de servir como presidente del capítulo estudiantil del American Concrete Institute en nuestra querida universidad. Leyendo el libro Charles Thornton, A Life of Elegant Solutions, comprendí como ingeniero civil y especialmente como ingeniero estructural la importancia de prepararnos para los grandes desafíos que nuestra profesión nos presentará a lo largo de la vida. La historia de Thornton Tomasetti es, sin duda, una de las más fascinantes de la ingeniería estructural moderna. Todo comenzó a mediados de los años 50 con la fundación de Led Zeppelin Associates por el Dr. Led Zeppelin. En la primavera de 1961, Vincent de Simone, egresado del Manhattan College, llamó al profesor de estructuras del joven Mr. Charles Thornton, el Dr. Vincent Vitagliano, buscando un estudiante interesado en trabajar ese verano en cálculos estructurales para edificios de concreto reforzado. Mr. Charles levantó la mano y el resto es historia. La empresa, que en 1977 adoptó el nombre de Thornton Tomasetti, se convirtió en sinónimo de innovación. En aquellos años, en el Manhattan College, Mr. Charles Thornton cursaba su último año, mientras que Mr. Richard Tomasetti era estudiante de segundo. Pertenecían a la misma fraternidad y desde entonces surgió una amistad que trascendería las décadas. Desde sus inicios, ambos compartieron una visión clara: no ser una empresa convencional de ingeniería, sino una organización tecnológica que aportaría soluciones innovadoras y elegantes a los retos estructurales. Su lema lo resume perfectamente: When others say no, we says here's how. A lo largo de su historia, Thornton Tomasetti ha dejado su huella en algunos de los proyectos más icónicos del mundo: instalaciones deportivas, hospitales, edificios institucionales y rascacielos que han definido los límites de la ingeniería, como el diseño de la torre Michelin-Belter, las torres Petronas, Taipei 101, la torre de Shanghái y la torre Jeddah, entre muchos otros. Más allá de sus notables logros estructurales, su legado humano es igualmente inspirador. El Dr. Charles Thornton fundó el reconocido ACE Mentor Program, creado con una doble misión: inspirar y motivar a los estudiantes de secundaria a seguir carreras en arquitectura, construcción e ingeniería, y brindarles oportunidades de mentoría y becas para que se conviertan en los diseñadores y constructores del futuro. Continuando con esta visión, la Thornton Tomasetti Foundation, establecida en 2008, promueve la educación y la investigación a través de becas, programas de apoyo y alianzas que fomentan la innovación y la excelencia en la ingeniería estructural y el diseño de edificaciones. Hoy en día, Mr. Richard Tomasetti se desempeña como presidente emérito de la Thornton Tomasetti Foundation, continuando con su compromiso de toda la vida con la educación y el avance de la profesión de la ingeniería. Por todo esto, es un verdadero honor y privilegio contar hoy con la presencia de Mr. Richard Tomasetti, un ingeniero visionario que junto a su amigo y colega, el Dr. Charles Thornton, impulsaron el desarrollo, la innovación tecnológica y el espíritu de colaboración que ha definido a generaciones de ingenieros estructurales. Su ejemplo nos recuerda que la ingeniería no solo construye edificios, también eleva las posibilidades del ingenio humano. Agradecemos su participación, les animamos a hacer preguntas y compartir sus inquietudes al final de cada conferencia, que esta jornada sea un espacio de aprendizaje inspirador y enriquecedor para todos. A continuación presentamos ante ustedes la conferencia titulada Why Concrete for Tall Buildings. Esta conferencia está a cargo del ingeniero Richard Tomasetti. La experiencia de más de 60 años de Richard Tomasetti como ingeniero estructural incluye numerosos proyectos de gran envergadura, desde el diseño del World Financial Center y las Times Square Tower en New York hasta el Plaza 66 en Shanghái. el primer edificio alto totalmente de concreto en China. Su firma ha sido la responsable del diseño estructural en algunos de los edificios más altos del mundo, entre ellos las Torres Petronas en Kuala Lumpur, Malasia, el Taipei 101 en Taiwán y la Shanghai Tower en China, y la Jeddah Tower, una estructura de concreto de 1.000 metros actualmente en construcción en Arabia Saudita. El señor Tomasetti es ingeniero civil del Manhattan College, donde también recibió un doctorado honoris causa y obtuvo su maestría en ingeniería civil en la Universidad de Nueva York. Es presidente emérito de las Urban Assembly Schools de la ciudad de Nueva York y ha formado parte de los consejos asesores de Manhattan College, Columbia University, Cooper Union, el New York University Sharp Institute for Real Estate y el New York University College of Arts and Science. Activo en el desarrollo de normas para la industria, el señor Tomasetti ha sido presidente del Comité de Edificios Altos de la American Society of Civil Engineers, miembro del primer consejo asesor del Código Sísmico de la Ciudad de Nueva York y coautor del capítulo 16 del manual de la ASC, Quality in the Constructed Project. Actualmente es director emérito del New York Building Congress y expresidente de la New York Building Foundation. El señor Tomasetti fue elegido miembro de la Academia Nacional de Ingeniería de los Estados Unidos en 2004 y fue el primer ingeniero en recibir el premio del capítulo de Nueva York del American Institute of Architects en 2006. Otros reconocimientos incluyen el Engineer of the Year Award de la New York Association of Consulting Engineers en 2002, la distinción Those Who Made Marks de la revista Engineer News Record por el desarrollo de la estructura tipo Stress Skin Tube para edificios de gran altura, el Leader of Industry Award del Concrete Industry Board en 1999 y el premio Eugene Smith a la redacción técnica por su artículo Novel Advance of Composite Concrete. Es profesor adjunto de la Universidad de Columbia, además de autor y conferencista activo. Coescribió el libro Exposed Structures in Building Design y el capítulo 22, Diseño protector de estructuras en la seguridad de edificios, en el Handbook for Architectural Planning and Design. En 2008 fue conferencista invitado en la serie Fazlur Rahman Khan Lecture de la Universidad de Ley con la charla Engineering of Major Architectures, Then and Now, y en 2012 junto con Charles Thornton recibió el Fazlur Rahman Khan Lifetime Achievement Award. Es un honor para mí presentar ante ustedes al ingeniero Richard Tomasetti. Hi, Mr. Tomasetti.
Are you ready for me?
Yes.
Oh, I thought you were going to repeat everything in English too.
Yes. Wait me a second, so, bueno.
No. It's all right. Okay, shall we start?
Yes.
Okay. Buenos dias. I'm sorry, that's all my Spanish. I'm delighted to be here at your university, talking to the students, and I assume some faculty members and anyone else who has come into this very interesting podcast. We want to talk this afternoon on why concrete for high-rise buildings or tall buildings. It's the same thing. Just a little test. Can you hear me okay?
Yes, it's okay.
Okay. All right. So you just go back and look at a little history, and you go back into the 60s and even up to the 70s, there was a feeling in the industry that if you're going to do a tall building, it most likely would have to be steel. For a variety of reasons, which I will be discussing, we learned that that's not necessarily the case, that concrete could be very competitive for tall buildings. And I want to take you through the reasons for that, both based on what was happening in the industry and both based on the material properties that we learned more and more about for concrete. So let's get started with that. Now, what I'm showing you here is the New York City skyline, but this was like 2010, just to show you how much things have changed. this is the New York skyline today. This picture was actually taken a couple of years ago. Now you can see there's three very prominent, very tall buildings in this picture. Extremely tall and extremely slender. They are all concrete. And one of the reasons they're concrete is because most of them are residential. And concrete works very well for residential buildings. And also because of the things we learned about building tall buildings with concrete, that in some cases, it makes more sense than using steel. Not to say that there's still a place for steel in many situations, but concrete has really been winning this race for the very tall buildings, as you can see in this picture, and even in the next picture. We won't get into identifying all of these because we don't have the time to do that. Right? But it's also an example how engineering and architecture get integrated, and how what the structural engineer is doing can influence the architecture. And these types of buildings have to be started with the architect and engineer working together at the very beginning. And that's including the mechanical and electrical engineers also, because the HVAC systems for these buildings and the elevator systems for these buildings are extremely high-end and extremely state-of-the-art, and you must know from the very beginning of what's going on. So integrating engineering and architecture is extremely important for high-rise, but not only for high-rise, for any major project. Now, if we go back a little bit and talk about traditional concrete, it was always seen for buildings of a certain height, and the flat plate was the big thing, just columns coming into a flat plate. And that worked very well for certain height buildings. But then to go higher, we realized we have to put shear walls into the buildings to resist wind loads and seismic loads, any kind of lateral load. And also we realize that if you do these shear walls in a closed form core type of situation, similar to the way you might do with steel, which is shown on the left, okay, you're getting even more stiffness from the concrete. And typically a concrete core will be stiffer than a steel core. But by using the core concept, we learned we can take care of other things such as torsion in the building, as well as loads coming in both lateral directions. But what else do you have to worry about when you do really tall buildings? It's not just a matter of how tall it is. It's the slenderness, the ratio of the height to the width below. Usually if you keep that about 5, you're probably in a pretty good case of saying, I don't have any special problems. As you start getting over 5, you start getting into pretty slender buildings, and you really have to take a closer look at everything. So slenderness is very important, especially when considering wind and seismic. And then the stiffness, and then the period. And even more important is understanding that most of these very tall buildings, the final governing parameter is the acceleration of the building during wind. Does the chairman of the board sitting at the top of the building feel any discomfort? That's what it all comes down to on a commercial building. Now, if you're dealing with concrete, you have other things to worry about besides the construction technology and cost effectiveness, but creep and shrinkage comes into the equation. So that's something you have to worry about more, and we'll talk about more later. And you don't have to worry about that as much with steel. And as I mentioned before, the architectural and the MEP is also extremely important. Now, on the right, you're seeing Plaza 66. Okay, that building, when it was done, I guess that's about 20 years or so ago, that was the tallest concrete building in China at the time. A very, very slender building. It's about 70 stories high and has very interesting history. We'll talk a little bit more about that a little later on. Excuse me. There's Plaza 66. So it's later on already. One of the real interesting things about this project is to show you the change in the state of the art. The Chinese codes had said at the time that any concrete building, okay, can't have a sway at the top, a deflection at the top, greater than L over 1,000. That's extremely, extremely severe. Very small deflection. And when you get into 70-story buildings, it's extremely costly to do that. So when we did this building, we had to meet with all of the authorities and convince them that that's fine for a 20-story building, or a 15-story building, but not for a 70-story building. And the governing thing was the actual dynamic behavior of the building, which you can get from a wind tunnel test. And we sat with them, and thank God some of our staff were very, very good at speaking Mandarin. And we convinced them that we should do a wind tunnel test, and then from that come out with the actual deflection at the top of the building, which after all was said and done on the maximum load was about L over 500, which is kind of the range that's usually acceptable in these buildings. L over 400 to L over 500 deflection at the top and maximum wind, okay, design wind is usually what we go for. Actually, it's the 10-year return is what we look at for comfort typically. The codes vary in different places. 10-year return is the maximum wind you would expect every 10 years. So the history on this was very interesting and kind of set the stage for doing tall concrete buildings in China. This is an example of the building before the facade was put on. And it was also in a very, very high earthquake area. So we had to do a dual system with a concrete core and a good resisting ductile frame on the outside. So we came up with this frame, and thanks to ACI, had all the benefit of the details that one should use in connecting beams and columns with concrete to have a very good ductile frame. So thank you, ACI. And that basically shows you what the design of the building was structurally, what you're seeing plus the core on the inside. Now, what is it about wind that we're concerned about? Well, you talk to the average person and you say you're worried about wind or you're concerned about wind. By the way, can everyone hear me? Am I loud enough? Nicholas, am I loud enough? Hello, can everyone hear me? I'm not getting any feedback, so I'm worried. Nicholas, can you hear me? Hold it, everyone. Okay, I just got a text that you can hear me. All righty. So most people think in terms of the direction of the wind, okay, is what you're concerned about. But that's not the concern. The concern is the cross-wind effects, and that's because of vortex shedding. So you all have probably studied some fluid mechanics, and you got a fluid, air's a fluid in this case, coming against the body, and it starts separating. And it separates on either side at different moments, okay? And those little curlicues, which are the vortex shedding, create little vacuums. So you start getting a differential pressure across the building, and that gives you a movement perpendicular to the wind. And then when the building moves, that aggravates the vortexes even more. And then the cycle kind of repeats itself, going back and forth. And that's probably the most major thing that affects the limitations of your high-rise building in concrete or steel. Now, one might ask, well, what about in the direction of the wind? The wind goes at a certain speed and then it slows down. Aren't you going to get vibrations in the direction of the wind? And the answer is yes, but they're not as critical. And if we had an interaction here, if I was in a classroom that I teach, I would ask you, why are they not critical? Right? And the answer is, picture the building moving in the direction of the wind, and then it moves back against the wind. All right? That's a dampening effect. It can only vibrate so much when it's in the direction of the wind. But when it's perpendicular to the wind, you can get very large vibrations. So when would we have very large vibrations? Well, just picture this. Picture that the vortex shedding vibration, so to speak, is close to the natural frequency of the building. Then you can get a superposition and you can get a resonance happening that could cause you a lot of problems. So you have to design in a way to avoid that. So if we look at this chart, okay, this plots the crosswind response of a certain project to the wind velocity. And you can actually calculate the shedding frequency, which is F in this equation, okay, times a Struhl number, divided by, times the wind speed, divided by the building width. But the secret here is you can't get this S unless you do a wind tunnel test. And that's what's really needed to do this stuff properly. Now, what the graph shows, if you solve for the wind speed, and if you're at this point on the graph, all right, where if you had no vortex shedding, this would be the line of movement. But when you have vortex shedding, if that's at the same frequency as the shedding frequency of the vortexes, you're going to get this bump in the curve. You're getting some resonance here. And this is what you have to worry about. So it's a lot of sophisticated analysis, working with the wind tunnel specialists to avoid this and get this to a point where you don't have that vortex shedding close to the frequency of the building at wind speeds that you expect to come quite often. So let's keep that in mind as we go further. Now, one might say, well, let's just make the building stiffer, all right? Well, that doesn't always work. You have to have it stiff enough so you don't get too many problems. But let's look at this equation, which is a simplified equation of motion for acceleration, right? And if you look at this equation, you can see that if you double the stiffness K, the square of the frequency is doubled. This term is doubled. Now, while the deflection is half, because the deflection is proportional inversely to the stiffness. So going back to the basic simplified equation up here, and this is simplified, acceleration is A times 2 pi f squared, okay? If you have this, if you have the A, but double the 2 pi f, okay, you kind of double the square of the 2 pi f, okay? You're kind of chasing your tail because one's going to cancel out the other, and it's hard to control the acceleration once you get to a certain wind speed. Give me a second. So, but if you would have complete equations of motion here, you'd have some other terms in it, like damping. And it's the damping that can solve this problem. And we'll show you how. This was a project that we designed and worked on with Harry Weiss. My partner, Charlie Thornton, was involved with this. And it was a proposed 2,000-foot tall building in Chicago. And what we did with this, and I'm sorry, there's no slide of it, but at the very top of this project in the wind tunnel, oops, it's not there, the wind tunnel, there was like a rod with a neoprene, like a neoprene rod with a weight that could slide up and down. And by sliding that weight up and down, it acted like a tuned mass damper. So we could control the damping in the model. So by studying this and controlling the damping in the model, let me show you what we learned from this. If you look at this wind velocity versus the peak deflection, all right? If you don't have the TMD activated, the tuned mass damper, you can see at the design speeds or before the 10-year return. We usually look for comfort at the 10-year return speed. But you can see before that, we got very, very high deflections, or could have been accelerations. Curve works for either one. And when we move that tuned mass damper on the model to increase the damping, we got all the way down here, which is below the acceptance level. So now let's look at that, putting in a percentage of damping. So the high point had a percentage of damping of 0.01. And then we changed the tuned mass damper and gave the percentage of damping of 0.02. Okay, so that's 2% critical damping. And I think most of you probably have courses and understand what critical damping is. And the other one is 1% critical damping. So that's the importance of this curve. 2 mass damper at 1%, you're all the way up here for the acceleration. 2 mass damper at 2%, you're all the way down here, almost at the acceptance level. Now, what's the significance of this relative to our conversation? Well, typical steel building intrinsically has 1% damping. A typical concrete building typically has about 2% damping. This is one of the major reasons why we're seeing concrete being used on very, very tall buildings, because of the inherent damping being much higher than the damping of a steel building. Most steel buildings that are extremely high, like some of the tallest, close to the tallest buildings in the world, okay, like 101 Taipei. I'll show you a picture of that later, but require very sophisticated tuned mass dampings. Yet currently, the tallest building in the world, okay, in Dubai, done by SOM, that building does not require tuned mass damper for the overall comfort of the building. And that's one of the main reasons why concrete is good for tall buildings and has become popular. Now, I'm going to leave you with that thought. And if you would all just understand, I'm not getting any younger, okay? I've got to leave the screen for just 2 minutes, and I'll be back. Okay, sorry about that. I trust you can all still hear me. If you can't, someone should send me a text. Okay, so
Okay, Mr. Tomasetti, continue.
okay, thank you so much. I'm sorry for the interruption. Now, before we go any further, I just want to mention that the other major thing that happened around the 70s is we started getting into really high strength concrete. So in earlier years, when you thought of concrete for tall buildings, the strengths were such, like using a 5,000 PSI concrete. I think that's 30-ish MPa or something. You'd have these humongous columns at the bottom of the building. Well, knock out the architecture, so to speak. But as we start getting into higher strength concretes like we have today, where we typically use something like 10,000 PSI, and some very tall buildings, we're using 14,000 PSI concrete, which I don't know, I guess it's 70, 80 MPa. We can reduce the size of the supports at the bottom. But we have some other tricks also. And here's one of them for wind. You may see sometimes how a lot of very tall buildings have a twist in them, like the Shanghai Tower on the left. So I want you to think about this. If the wind is hitting this building that's twisted, at every level, it sees a different cross section. So you don't get this vortex shedding support from level to level. The frequency of the vortex shedding at one level is a little different than the frequency at another level. I'm just checking something here. I want to give you a term. Okay, so this use of twisting the building reduces the effect of the vibrations from vortex shedding because they're changing all the way up. So you don't get as much force from those vortex sheddings adding to the vibrations. And another thing is, if you put some rough surfaces on the building, like on the right, you see Taipei 101, and you see these jagged things here, the rough corners. That tends to break up the vortexes also. So if you can break up the vortexes, you don't get this synchronicity going up and down the building. Sorry, my mouth is dry. But so this is a perfect example of integrating engineering and architecture. And you see this in many buildings, even going back to Gordy's design, Sagrada Familia, the roughness of the building helps. The fact that the building is changing its shape as it goes up. You see it in the Petronas Towers, okay, and you see it in the Kingdom Tower, which is under construction now, which will be 1,000 meters high. Yes, I didn't say feet. I said 1,000 meters high, and I'll show you a little more on that in a few moments. Okay, so that's another reason why we can, for both steel and concrete, go higher as we learn how to integrate the architecture with the engineering to give you an aeroelastic design, so to speak, that minimizes the synchronicity of vortex shedding. So it varies, the frequency varies a little bit as you go up the building. But there's one more thing I forgot. And I bet there's some people in the audience don't even realize this. As you increase the strength of concrete, you also increase its modulus of elasticity. So it gets stiffer. And that also helps in using it for tall buildings. And it's not a direct proportion. It's proportional to the square root of F prime C, the strength of the concrete. But that's another help that we get through the technology of developing high strength concretes. Not just higher strength, but higher stiffness. So in addition, getting the higher damping, we get a formula that makes concrete very attractive for high-rise buildings. Now, many years ago, we did this study with Caesar Pelli, the Miglin-Beitler Tower. My partner, may he rest in peace, Charlie Thornton, was very proud of this project that we did. And it was a study to do I think it was almost 2,000 to the top of the building, yes, to see how we can get it to work in concrete. And what came out of that study was the realization that forget columns and shear walls, okay? Let's just use walls. Concrete wants to be a wall, all right? And for high-rise buildings. And you can see with this section that we had these massive walls, but they didn't take up that much room at the bottom of the building because of the way they were oriented. And now this has become very popular, and I will show you with the current very high-rise buildings, even though this one wasn't built, this kind of effect was taken. And with the present tallest building in the world, okay, done by SOM, with Bill Baker as the structural engineer, okay, they came to the same conclusion, and they used this wall concept in their design. And like I said before, we put this in a wind tunnel study, to study and get all the parameters we needed, as I was talking about before, which is basically you have to know the different mode shapes. And the three most important are translation in one direction and then translation in a direction perpendicular to that. You see that here as Y and X. And then also the torsion, because something can vibrate in torsion. I'm just checking our time here. Something can vibrate in torsion. So you have to be aware of both of them. And this is what you get out of the wind tunnel test. And you use this along with testing for damping. This is an example of a wind tunnel test done on another project, the Chicago Spire. Unfortunately, this never got built. But basically, if you're not familiar with wind tunnel testing, you build the model, basically a static model, and you put it into wind tunnel test. It's just a rigid piece. And then you simulate the surrounding areas that are close to it. And then you put in the back area here, you put a kind of roughness that simulates whatever else is near here, but not too near. And through using these wind tunnel tests and the initial calculations you give to the wind tunnel designer based on the frequency, the stiffness and everything of the building, you can come up with what the acceleration of your project is. And there's restrictions on acceleration. So, for example, if you look at this chart, in North American practice for the 10-year win, which is one of the most popular ones you look at, okay, for a residential building, you want to keep the accelerations in the 15 to 18 milligee range. No more than that. Hotel is kind of similar. And in an office building, okay, you can keep the accelerations slightly higher, okay, which is a good thing for steel, because steel works well with office buildings, and you can get a little higher acceleration there. But not if you're going to go to 1,000 meters, that's for sure. Okay, and the reason for these differences is that in a residential, you're sleeping, you're laying down on a couch, you're relaxing at home at night, and everything's very quiet. So you're very sensitive to any accelerations. In an office building, you're running around, you're busy, you're working, people interacting with each other. They're less sensitive to the accelerations. So you can have more accelerations. So these are all the things that typically are the final governing thing on a very, very tall building. And concrete does very well because of its stiffness. It's increased stiffness as you increase the strength. Most important, it has increased damping compared to steel. Now, just very quickly, if you do need a two-mass damper, there's various ways of doing it. There's like a single pendulum that goes back and forth. It'll go back and forth in the opposite direction that the building wants to go, so it causes a resistance. This happens to be a picture of the it's like brass colored steel on the top of 101 Taipei, okay? And it really is like a thing to see. And that building's all steel primarily. And they actually use it for a show. People can go up there on a windy day and watch it move back and forth. Now, let's look at some of the real current things happening. This is the building we're doing in Saudi Arabia. Okay, its total height is going to be 1,000 plus meters. And you can see how it's tapering on the way up. And you can see that the cross section at every level is different. So you don't get this this coherent vortex shedding that I was talking about before. The frequencies of the vortex shedding change as you go up, so you get less reinforcement. And this will show you that the height to width aspect ratio is 12:1 for this building. Remember what I said, if you're like 5:1, you probably won't have too many dynamic problems. Well, this one breaks many of the records. As does Burj Dubai, which is the SOM building, okay, which is currently the tallest building in the world. But now look at this. This is a cross section showing the basic construction. And you can see, it's what we talked about before, it's walls. You don't see any columns. There's no columns. The walls act as walls. They act as shear resistance. And the walls are the columns. And it's all walls and columns. And that's how the project was accomplished. I love this little thing because it's a three-dimensional view of a typical floor, which shows you how all the walls are connected with link beams, because you got to have ways of getting in and out of the walls. There's no column transfers. It's all flat plate floors, not even spandrel beams. Very, very simple construction. Now, I would be a naughty boy if I didn't give some credit here to our contracting friends, because they have made a major contribution, and the people who make the concrete equipment. There's been great advances in the pumping of concrete that have allowed these very tall buildings to be built. You know what concrete is like, and it's kind of a very heavy thing. Just picture bringing it up several hundred feet or more. You need good pumping technology. And that was another advancement in the industry, which helped in making concrete more popular for high-rise buildings. And here's just an example of how you do this. You don't need the high-strength concrete everywhere. As you can see here in the foundations, it's only 9,000 psi or 60 MPa. Okay, at the lower levels, all right, you see 12,500 psi or 85 MPa, and near the top, it's only 11,000 psi or 75 MPa. So you can use the different strengths of concrete at different parts of the building to economize your project as much as possible. And this shows you the kind of studies that you do. The three lines on the bottom are studying the amount of damping. Okay, and you can see it goes from 5% damping with the blue line to 1.5% with the black line. Now you have to do these kind of studies because you will never be able to calculate the exact damping that you have in your building, number one. So you'll have to box it in a certain range. And you can see that was done very well here. Between 1.5% damping and 2% damping, which you should get with a concrete building, all right? It's these two lines here. And this is some of the criteria for office by the international standards and for residential, so it's well within that. And RWDI is a very well-known wind tunnel consultant. They have their own studies where they feel you can go even higher in some of these in some of these projects. But this project we're talking about here, whether it's 1.5% or 2% damping, we're well within those requirements to maintain the comfort of the building. And here you can see the building being built. It stopped for a while. This is in Jeddah, Saudi Arabia, using jump forms going up. Very repetitive. In one way, it's a complicated design, but what you want to do is have a complicated, very, very simple, sophisticated analysis. That's what we do as engineers, to come up with a very simple construction approach. And this is very repetitive as it goes up. You use the jump forms. And this, I think, is pretty current. It's a little higher than that. They've gotten back to building the building, and maybe within a year or so, okay, it'll be completed. I don't recall the exact date that they have for completion on this. Now, another interesting thing about concrete, it's very friendly. It doesn't mind working together with steel. And KLCC, also known as the Petronas Towers, which we did. At that time, this was the tallest building in the world when we did it. Okay, it's basically a concrete frame around the outside and a concrete tube on the inside. Here we did actually use columns for a variety of reasons. It made sense with the with the architecture. So this shows the project going up. It's got a little building on the side. Each one has a little building on the side, and then there's the main building. But what's interesting here is that it was combined with steel. Because there was a lot of office space in this building, steel has certain advantages on the floors. You want to break through, you want to hang air conditioning, you want to do all sorts of things in an office building that you don't do in a residential building. And steel makes a lot of sense there. But you don't have to do the whole building in steel to get those advantages. So this shows concrete is the main primary structure, and all the floors are done with steel and standard deck and concrete topping on them. And the other smart thing that the contractor did here, that the owners did, they picked two different contractors. So it became, for each of the buildings, it became a race to get to the top. And one contractor, he couldn't come in with excuses, asking for extras, unless the other contractor did. So each one was trying to show that they were doing a better job, and it worked out very economically for the owner. That's kind of an aerial view looking down on it. What you can see from this view, the roughness, so to speak, of the outside, is, and how that really helps break up the vortex shedding to reduce the amount of damping that's needed. And here's another example of concrete and steel being used together. This is Tampa City Center. At the time it was done, it was the tallest building in Florida. And we used a concrete core and a steel frame around the outside. Now, the one thing you have to be aware of, especially when you use a concrete core with a steel frame, is concrete creeps and it shrinks. So as you're building this here, the concrete, as it's curing in the center, is like tightening up. It's deflecting. It's getting compressed, and it's creeping. Steel doesn't creep. Steel only creeps at very, very high temperatures, and we leave those problems to the people in aerospace when they're re-entering or something. So one disadvantage with the concrete, especially if you mix it with a steel frame around it, it creeps, and you can get differential shrinkage, and at the top of the building, and differential creep between the core and the steel on the outside. So you have to study that. This is just a quick a curve that shows that. Okay, we won't go into the details, but the bottom line of this curve is, as you keep putting on the floor, okay, you get some elastic deflection, and then the curved part, as you keep putting on the floor, this is the extra deflection you're getting due to the creep and shrinkage of the core. Okay, so this is a prominent thing that happens when you combine steel and concrete as a steel core. A steel perimeter structure and a concrete core. Now, the other interesting thing is that it goes on for a long time. So you've got to get this to a point that it's not a problem when you leave the project. And the way that's done, which this little cartoon shows, is creep compensation. So while the project's under construction, you have to work with the contractor, and you design the project so that the core is slightly longer than it has to be compared to the steel columns on the outside. So as you go up, and this is creeping down, eventually they get to a point where they're coming to the same point. Unfortunately here, the C executive at the top might still be disappointed with this sketch, but we'll blame the draftsman on that, okay? Because it's not exactly flat, but it should, but it should be. But this is how you avoid this problem, using this creep compensation as you go up. Now you might ask, if the building is all concrete, do you also have this problem? And some will say, well, no, it's all concrete. Why would you have a differential between the outside frame and the core? The answer is, when you get to very, very tall buildings, okay, you do have this problem. And the reason is that even if the stresses that are there all the time are a little different on the outside and the core, the stresses that are there all the time are the ones that give you the creep. Stresses coming from wind don't give you the creep. It has to be there constantly. That's one thing which is somewhat of a contribution to this. The other thing is that you're talking about differential creep and shrinkage. And shrinkage, how the concrete shrinks, is a function of its geometry. So if you put two pieces of vertical concrete next to each other, so to speak, if they have different ratios of surface area to volume, they're going to shrink at different rates because of the temperature coming in at different rates, and you get a differential shrinkage. So on these very, very tall concrete buildings, you still have to check out the differential and come up with a situation where you're following the concrete as it goes up to make sure that all the columns on the perimeter and or walls, whatever you're using, and the walls in the core all wind up at the same level when you're finished. And this takes a lot of cooperation between the engineers, architects, and the contractors. But not to blow the horn of concrete too much, which I'm sure ACI, you're a group associated with ACI, loves, but I got to live with the steel people too. So I want to end by saying there's always a place for steel and there's always a place for concrete. And bless these two industries, they really know how to compete with each other. And their competing with each other has caused tremendous advancement in the art of design and construction that allows us to do so many of these beautiful projects. So it's not just a matter of the architect and or the engineer, it's the fine work that the suppliers are doing, the subcontractors are doing, and the general contractors are doing, and the equipment makers are doing, such as pumping of concrete, that make all of this possible. Whether you're Eiffel and you choose steel, or you're SOM and you choose concrete, as was chosen for the current tallest building in the world, Burj Khalifa, you wind up with a good design because of all of these parameters working together. So at this point, I think I've covered all the things I want to talk about. I'll just mention one other interesting thing. When we did the Petronas Towers, we actually built a plant working with the contractors. They built a batching plant right on the site because that concrete was not available there, right? So you can solve that by having your own batching plant. Also, it affects the choice between concrete and steel. You go to a lot of places in the world and they don't have steel fabricating plants. And so then you're being pushed towards using concrete. But in summary, the main reasons why concrete is so popular for very, very tall buildings is because we've gotten the strength of the concrete up. It's because of the internal damping that you have in the concrete. And it's because of the fact that as you go and get higher and higher strength concretes, you're also getting higher stiffness of the concrete. So I will leave you with that and be delighted to answer any questions that you may have. Thank you. Nicholas, where do we go from here?
Hi, Mr. Tomasetti.
Hi, Nicholas.
Excuse me, a delay with the window. Okay, so we open the chat to questions about the lecture with Mr. Tomasetti. Between the participants, write your questions. I'm going to tag one question for you, Mr. Tomasetti, and in your career with Mr. Charles Thornton, what project would you say marked a turning point in your career and why?
Oh, the beauty about having worked with my partner and worked with Dr. Lev Zetlin, who was the very original person who started this firm. When I joined it, there was only like 40 people there. Now I'm retired, but I'm still have some activity with the firm. I'm proud to say it's 2,000 people. It's very, very hard to say which one is the best one, but to the chagrin of the steel industry, I'll probably have to say it was the American Airlines jumbo jet hangars, where we developed these 230-foot cantilevered steel deck hyperbolic paraboloids with no structural steel to cover 4 747s. That was one of the major highlights in my life. Okay, and then I would say at this point, later on in my career, all the very super tall buildings that we did. It's hard to say one was more interesting than the other.
Okay, thank you, Mr. Tomasetti. Another question for you is, what do you think about artificial intelligence? Do you believe artificial intelligence will play a significant role in structural design and in the professional responsibility of engineers?
Well, why don't we ask ChatGPT that question and see what they say?
Yes. Yes.
The answer, I think, is yes. Okay. My mentor, Dr. Zetlin, always had a saying that people probably would have been happy living in caves if we still stayed in the caves. But technology is here to stay. So I think you have to learn to live with AI. And I think we can use it to allow us to do less work and more thinking. And we can be even more creative than we ever were before. So will AI play a role? Yes. The more important answer is that it's already playing a role. I can see it with my students at Columbia, how they will rely on AI, okay? we try to match up their results when they send in an essay or something to see if it says the same thing. But it's here to stay. We have to learn how to use it the same way we learned how to use the computer analysis when they first came out. All right, where you learn it, you just can't take something from a computer run and believe it 100%. You have to learn how to do little calculations on the side to check it, okay, and then see if you're getting the right answers from the computer. The same way we all thought that we would ever understand math anymore when we invented the hand calculator. Okay, so I think it's here to stay, and I think it's going to be a great thing. There's so much that you can do with it.
Okay, thank you, Mr. Tomasetti. Now we have question by if the Tomasetti. Is there an overall awareness of the benefits of using concrete, or an unknown pushback due to the lack of education in the industry today?
I'm sorry, could you repeat that, Nicholas?
Yes. Is there an overall awareness of the benefits of using concrete, or an unknown pushback due to lack of education in the industry today?
Is there an overall benefit of using concrete due to lack of information in the industry today? Is that what you're saying? I don't understand it.
I'm going to write in the chat.
Mm-hmm.
If you want, go back to the window of the platform.
You think I know how to do that?
Yes.
Well,
Yes.
first, let me end the show here.
Okay. I'm going back to StreamYard link window with Microsoft Edge.
Now that's not coming up right now. Well, let's not get hung up on the computer. Just repeat the question one more time.
Okay. Is there an overall awareness of benefits of using concrete, or an unknown pushback due to lack of education in the industry today?
Okay, no, I don't think there's an overall information of the benefits of using concrete. I would say that many are not aware of the specific benefit for like using concrete for high-rise buildings, I would say. But I would also say that the people who are designing high-rise buildings, okay, because not everyone's designing high-rise buildings, that they have enough awareness of it. ACI does a great job in promoting concrete, so there should be enough awareness of it out there. Maybe ACI can do a little more by promoting the use of specific projects as opposed to all the details of how concrete behaves, but that's also very, very, very important.
Okay, thank you, Mr. Tomasetti. Another question is, what advice would you give to young professionals who want to contribute to the advancements of structural engineering at a global level?
At what level?
A global. I repeat the question. What advice would you give to young professionals who want to contribute to the advancement of structural engineering at a global level, like Thornton Tomasetti makes?
Well, my first advice is you've got to get your master's degree. Okay, you're not going anywhere if you want to work on interesting projects, you're not going anywhere with just a bachelor's degree. Sure, there's exceptions. There's always exceptions. There's billionaires out there who never finished high school.
Okay.
But those are exceptions. But I would say you have to get your master's degree, and then study all your course options. Take the courses where you really need a professor to help you. And if it's a course that you feel you can get just about everything out of it by reading the text yourself, take a little more complicated course. Okay? Don't go the easy way, go the hard way.
Okay, Mr. Tomasetti. Thank you. And last question is about what is, in your words, the legacy of Mr. Dr. Charles Thornton and you for the history in structural engineering?
I'm sorry, say that again. What is the legacy? I'm sorry.
In your words, what is the legacy of the life of Mr. Dr. Charles Thornton and you, Mr. Richard Tomasetti, of the legacy in the structural engineering, in the field of structural engineering?
Oh, the legacy that we leave behind?
Yes.
Well, I'm not ready for my legacy. Unfortunately, Charlie passed away very immature, in an inappropriate time, quite young. He was only 83 or 84. But I think the legacy, and I hope I would have one as wonderful as his, I think the legacy is always knowing that what you're doing is for people. All right. And there's a great engineer and professor, George Winter, from Cornell University.
Yes.
Okay. Many of you may recognize the name. And he had this saying that we have to remember that buildings are for people, not for the engineers, not for the contractors, not for the subcontractors, not for the architects. Buildings are built for people. And we have to keep in mind that everything we do is for people, number one. The other thing I would say that's important is, and I think you quoted something Charlie said in his book, being open to new ideas. Okay.
Disruptive idea.
Yeah, not oh, that's hard, we can't do it, always how can we do it? How can we do it? Not how can't we do it? Okay. And just don't be afraid to push your ideas if you have something unique. I think. And then the other thing I would say for all students, when you get out there and work, whatever firm you're with, act like it's your firm. Don't get hung up on what the benefits are, what this is. Okay. Don't get hung up like, well, that doesn't affect me. So-and-so, someone else is going to do the calculation. You be interested in everything that affects that project, and always do things that are in the best interest of the design and the best interest of the project, not that are just in your interest or your firm's interest. If you do things that are in the best interest of the project, you'll help have that project go smooth, and you'll help the relationship between you, your firm, and the project's client.
Okay, thank you, Mr. Tomasetti. So, closing remarks, a special thanks to engineer Mr. Tomasetti for his time and dedication to this event at National University of Colombia. It has been a wonderful experience for both our student chapter and the university. And we will also like to express our gratitude to everyone who joined us today and to all those who supported the promotion of this event. Our appreciation goes to the professors of the structural engineer line of the civil engineer program, the graduate program in structures, the member of the student chapter, the curricular area management of civil engineer, and the faculty of engineer of our university. So in conclude, I leave you with these words from engineer Charles Thornton. Engineering at its core is about shaping the future. It is through our collective efforts that we have the power to create structures that not only stand tall, but also stand as reminders of human ingenuity. So thanks, Mr. Tomasetti. It's a great opportunity for us, and I hope you stay here well with us.
And I want to thank everybody for listening, and I'm delighted to be here. I wish you all the luck in the world, and for the faculty as well as the students for their careers. And Nicholas, I want to thank you also for your tribute to my partner, Charlie Thornton. I knew him for more than 60 years, and it's just been very sad that he had to leave us so soon. Thank you all.
Thank you, Mr. Tomasetti. For me, it's a great honor. So, bueno, muchas gracias a todos por acompañarnos y nos vemos en una próxima oportunidad. Feliz tarde. Don Mauricio.